Hello, my name is Daniel Kevin Siboro, and today I'll be presenting my summary regarding this week's topic of my wireless communication and convergence network course. And this week's topic is about signal propagation and path loss models. And in this topic, I will be covering signal propagation and propagation characteristics, and also various path loss models such as free space models, two-ray models, and millimeter wave models, and other models. So let's first talk about propagation characteristics. So there are several propagation characteristics, and propagation characteristic is a factor that we need to know about signals when we are transmitting them from our transmitter to our receiver. And as an example here, we have an antenna transmitter, and it is going to transmit signal to the car, to this car right here. And so the first propagation characteristic I'm going to talk about is path loss. Path loss model is described by this blue line, which essentially means that there is a direct, straightforward path towards the receiver. And here we characterize the propagation by finding the ratio of the received signal to the transmitted signal over distance. And we see from the blue line that there is a very slow change of this ratio. And we see that the change is quite smooth. And the next characteristic is called shadowing. So shadowing is caused by an obstruction from an object, for example. So here, this red box represents the object. And how does this object affect the signal? So here we see the red line that has fluctuations. It is different from the blue line. It has fluctuations, but the fluctuation is quite slow. We see here. And then the next one is multipath fading. Multipath fading means that the signal that goes into the receiver comes from many different paths, or for example, from many different reflections from objects from the environment, or also refractions and scattering and such. And here we can see that from the green line here, the fluctuations are more frequent than the red one, and the ratio is not exactly consistently decreasing over the distance. And this is an important factor to consider when we are, for example, designing a signaling system, because this line right here, the green line, makes it unpredictable. So why does the signal being unpredictable make it bad, or makes it inferior to shadowing or path loss? Well, here's the thing. We can see that the line has a lot of fluctuations, and it's frequent and it's fast, as the graph describes. And so it is hard for us to tell how the receiver should behave when it receives the signal. So for example, with the blue line, we can say that, oh, for example, detonation is 5 times or 10 times, because there is a consistent, or there is a smooth transition of the ratio over the distance. It decreases slowly, right? But with multipath fading, it is not exactly possible to exactly tell how the transmitted signal behaves. And so here are some path loss models. And maybe the first thing that comes to mind is Maxwell's equations, because signals are consisting of an electromagnetic wave. And Maxwell's equations describe how electric fields and magnetic fields relate to each other by these sets of equations right here. But the thing about modeling with Maxwell's equations, just from seeing the equations, is that it's quite complex. And it might not exactly be practical to constantly use Maxwell's equations when we're trying to design our system. And so there are several other models like free space model and two-path model, ray tracing models, the single slope path loss exponent models, and the measurement-based standards model. And I will show an illustration for some of these models here. So here's the free space or loss model. Loss meaning line of sight, because the transmitter has a direct straightforward path to the receiver, as we can see with the blue line. And the next one is the two-ray model. The two-ray model, compared to the free space model, considers a reflection from a certain object right here. And maybe you may think that these two models are quite simple, or maybe not exactly realistic to how signals propagate in real life. And you're right. These two models are too simple for designing systems that transmit signals in a crowded area, for example, in a metropolitan city, for example. And so it might not exactly be appropriate to use these two models unless it's a very simple system. And so the next model is called the general ray tracing model. And although it looks complex, but it's actually not very hard to understand, and it can actually resemble how signals around us are being propagated. And here there are several colored lines that has been described. So the red lines are reflections, the blue lines are scattering, and the green lines are diffraction. And here we can see that there are many ways for signals to be propagated and then received by the receiver. For example, scattering can scatter the transmitted signal into many different other signals, and they can still be received by the receiver. And then next is the simplified path loss model. This model is usually used when path loss is dominated by reflections. And this is the equation we can use to model the signal propagation. And the parameter for using this model is to have the gamma to be within 2 and 8. And here is an image that shows frequency allocations in the United States. And there may be some services that you're familiar with. For example, radio, there's AM and FM, and there's TV broadcast, 3G or 4G cellular, Wi-Fi, 5G cellular, and there are also maybe some that's not very popular, like WiGig or CMOS IC. And how you can read this image is that each bar here, for example, like this is one bar. Let's say this is one bar. The one bar goes from a low frequency to a high frequency. And so this is, for example, the first bar, second bar, third bar, and so on. And we can see here that the radio is used in low frequency and also the TV broadcast. While, for example, our cellular technologies like 3G or 4G is being used in slightly higher frequencies, and also Wi-Fi, for example, 2.4 gigahertz. And what I'd like to point out here is a technology called millimeter wave. Millimeter wave, as its name, is a technology that uses signals of very small wavelength, or as its name describes, millimeter wavelength. And what this provides us is high frequency signals, which offers high data rate. And millimeter wave is located between 60 gigahertz to 100 gigahertz. But currently, only a few commercial millimeter wave systems occupy these frequencies. But why? Well, there's a problem with millimeter wave propagation. Although it comes with high data rate due to its high frequency makes it also vulnerable to attenuation or absorption from molecules in the air. For example, from water due to rain, or even from oxygen. And here from the left graph, we can see there is attenuation from, for example, here we can see some peaks from H2O, and then there's some peaks from oxygen here, and there's other peaks from H2O as well. And this makes it a problem because we'd like high gain so that the receiver can properly manage the signal, properly process the signal. But then it's hard to do it when there's all this attenuation. And from the right graph, we can also see specifically rain attenuation based on the amount of rain. And so here we see with higher frequency, there is higher attenuation, although it does saturate at a certain point, it doesn't always increase. But we can also see that with lower frequency, there's less attenuation. And this is the problem with millimeter wave propagation. But there is a way to tackle and somehow model millimeter wave propagation. Millimeter wave propagation models currently are immature, meaning it can't exactly be used with 100% certainty. And so it requires very specific parameters to be considered with the model. And here I would like to introduce empirical channel models. So what are empirical channel models? Well, they are models based on measurements or experiments where you obtain a lot of data and then you model signal that's propagating using that data. And it is usually specifically for a certain site or for certain frequencies. And so, for example, here, the Okumura and Hata model, where the Hata model is sort of like the next model or sort of like the improvement for the Okumura model, are models used or created or modeled in Tokyo. So this is site specific, and so it is also frequency specific, as in it only takes in the frequencies used within Tokyo. And there are also other models, like for example, the COS231 model, which is the HATA model, but uses an extension of frequency of up to 2 gigahertz. There's also the multi-slope model and also the Waldfish or Bertoni model, which is a model based on the COS231 model, but considers diffraction. Currently, empirical channel models are also being used, for example, with LTE or 4G and 5G. And for example, for 5G, the model is based on 5G frequency, for example, of up to 100 gigahertz, for example. And also for Wi-Fi channel models, for example, for 40 megahertz channels, these are some empirical channel models we've had. And here I'd also like to sort of show how signals are transmitted or received. So transmission and receive. So for example, we have a digital input, which will go through modulation. So modulation as in QPSK or BPSK and others. The result from this process is an analog signal that we can, for example, represent as PT. For example, this is analog. And from here, this signal requires the carrier signal. Or for example, for Wi-Fi, it would be 2.4 gigahertz. And then from here, it will be transmitted. And when we're transmitting a signal, we will use a certain channel. So for example, there's a certain channel here, and then there will be a receiver that will receive the signal. And so let's call this YT. But how exactly do we find YT? Well, this channel actually has its own equation as well. So for example, let's call it QT. And YT is a convolution of QT and also PT. Or we can also model it with the frequency. So for example, we will have something like this. So here, this is the carrier frequency or 2.4 gigahertz. And so this is how transmission and receiving works for signals. Before ending this video, I'd like to say that all the pictures used in this video is from my lecture's presentation or from the internet. And thank you for listening to my presentation, and God bless you.